Hi, so everyone is here.
Yes, ma'am. Right.
Okay, any questions from previous lecture? Yeah. Did any of you got in touch with Nirankush by any chance?
No, ma'am.
No,
Oh. Okay. So then shall we start?
yes,
Yes,
Okay, and also just this group which we were having. So do I have the permission? Okay, Ridhiman, you are the group admin for this generating functions. Can you remove this last person?
yes. I am also making you the admin.
Okay. So I got in touch with this fellow and the person won't be continuing. So there is no point keeping the person here.
Okay. Yes, done.
Okay. So rest of it will come here anyway. All right. So is my screen visible?
Yes,
So in the last few lectures, we have been seeing sets and multisets and how they can be represented, etc. Today, and in the just the immediate lecture, we saw permutations of sets, right? Various ways of representing a permutation, how it can be um, further subdivided into alternating permutations, reverse alternating permutations, etc. We talked about descents, their Euler number, and many such parameters, right? For the permutations. And all those permutations which we dealt with, they were the permutations of a set, correct?
yes,
Now, if we want to deal with permutations of multi-set, then what happens? Do I have all these concepts ready in my hand? Do I have to manipulate something? What all information as it is gets carried forward when I shift my gears from a set to a multi-set? Okay, so that is the main topic for today. And once we have understood this, then we will see just how we had different ways of representing a permutation of a set. We'll see how a permutation of a multi-set is useful when we want to deal with partitions of a natural number. So you see how many times like we have been seeing the partitions or ways of writing a number. We have dealt with this, I think, twice before or thrice maybe, and today again we'll deal with it. And then depending on, not really depending on, we'll further take the information from there to the point when we will understand what a Young's diagram or a Ferrer's diagram for such partitions are. Okay. So let me start with this. Yeah, okay. Before we actually start, so actually the assignment is pretty much ready. So do you want me to release the assignment tomorrow or after the quiz?
After the quiz.
How many people are saying that?
Anything is fine for me, ma'am.
Okay.
Same.
Sam?
Anything is
Okay, so majority says anything is fine, so we'll go with that.
Okay.
Sorry, Ridhiman. But anyway, the submission deadline would be post quiz, so that should not be an issue. So today is what, Friday? Tomorrow I'll release it. So let's say next Saturday will be the
Okay.
submission deadline.
ma'am, if Riddhiman has a problem, I can go with him.
Oh,
No,
so-
it's fine. No, it's nothing like that. I just said if there that was the option, so I would choose. But it's not like I have some big problem or anything.
yeah, I understand. That is why I conveniently chose the poll with higher votes. If it was a problem, I would have considered it. Nevertheless, you guys are smart. I know you people anyway do it in last 2 days. So it's not like if I give it after the quiz, it makes any difference. Or if I give it now, you'll have more time. Right? I have been a student. I know how things work. As in how students work. Okay, so let's start the permutations of multisets. So as before, let M be a multiset and then W be a permutation on this multiset M. Then the descent set of W can be defined just as we defined earlier, that Wi is bigger than Wi plus 1. So you may have questions. So earlier, remember we had the two sets, the set of descents of W and the set of ascents of W. And it was very clear that if something is not a descent, it has to be a ascent. Why? Because given any two numbers, either one of them was smaller than the other or the other way around. But now when you're dealing with a multiset, there can be a possibility of hitting two numbers which may be equal as well, however appearing at different locations in the permutation W, right? Just how you have a word generating. So E appears in two different locations. Okay.
Yes, ma'am.
So in that sense, now we will, the information which we lose is that we cannot say anything which is not in the descent set has to be an ascent for W, but certainly we can define the set descents. And it collects all those locations where the Wi is bigger than the next element. Okay. So this is just to see the contrast, and we'll immediately shift into proving more important results. But so while writing, I just did a sort of mistake. So this number which you see here, it's a n choose k, but there's a q in the subscript. So what is this notation actually? Let's first see that. So n choose k sub q is the q factorial of n divided by q factorial of k multiplied q factorial of n minus k. And this q factorials is actually this number, that if you take a natural number n and then q is any variable or like actually a number, so then q factorial of n, so far okay, let me finish this. So q factorial of n is 1 plus q, 1 plus q plus q square, and so on. This product goes on till 1 plus q plus and so on till q of n minus 1. So the last term has n terms. And there are in total of n such terms. Okay. So you see that if I put a q equals 1 here, then I obtain my original, excuse me, factorial. Because this will be 1, this all will be 1. So I will have a 1 plus 1, 2 here, a 3 here, and ultimately a n here. Okay. If you want, you could have put a 1 here to make it more consistent with the original definition of factorial, and then you would have gotten. So why I have not written it here is that then to match it with this particular notation, I should have put up 1 plus q raised to 0. But q raised to 0 is going to give me 1, right? So that is not something which works for me. So that's why you put a 1 here, and then 1 times 1 plus q times 1 plus q square times 1 plus q raised to n minus 1. And when you would put q equals 1 in this entire thing, this is nothing but n factorial, right? Because you would have a 1 multiplied by 2 multiplied by 3 and so on up till multiplied by n, right?
Yes, ma'am.
So this new n choose k sub q is actually this number. So it's a q multinomial coefficient. So this, remember, something like this we could have also written as n choose k comma n minus k. We discussed this earlier. So n choose k is same as n choose n minus k, and therefore to keep it consistent with the notation for multinomial coefficients, we could have written n choose k as n choose k comma n minus k. Therefore, this would make more sense if you would have written this as a multinomial n choose k comma n minus k, but it's a with a q factorial. All right. So such a binomial, or rather a multinomial in this case, is a q multinomial coefficient. All right. So far we have seen binomial coefficients, then we generalized it and saw multinomial coefficients. Now we have seen something called a q multinomial coefficient, which is this. So here it has appeared with just 2 terms, but you could have had a n choose a1, a2, am sub q, and that would translate to n q factorial of n divided by q factorial of a1 times q factorial of a2, and so on. All right. Where the sum of these ai's should have been n. Is that okay? Should I
Yes, ma'am.
move forward? Yeah, please tweak up. If there is any confusion, I'll elaborate further, or I'll give you time to uh, grasp this.
Can you repeat the last line, like the AI you mentioned?
So let me try to share the other one. Which lecture it had? Okay. Yeah. So lecture. Just a moment. Are you able to see lecture 10 now?
No, ma'am.
No.
Now?
Yes.
Yes.
Okay. So here we talked about this multinomial coefficient n choose a1, a2, am, right?
Yes. Ma'am.
With these a1, a2, am summing to n, right?
Yes.
If you had just two terms here, a1 and a2, it was n choose a1 comma a2, which was nothing but n choose a1. Correct? So that was the binomial coefficient. Then we dealt with this, which is the multinomial coefficient. So you remember this actually was n factorial divided by a1 factorial, a2 factorial, and so on until am factorial. Right?
Yes. Ma'am.
So in this extension, now we are defining the Q multinomial coefficients. So this was the multinomial coefficient. And similarly, if there were just two terms, it was the binomial coefficient. Now we have Q binomial coefficient, or rather Q multinomial coefficients. If I know what are Q multinomial coefficients, keeping the number of terms here restricted to 2 will give me the Q binomial coefficients. Therefore, we now directly see the Q multinomial coefficients, and they are defined as, so if there was a Q here, if there was a Q, let's see here, then all these would have been the Q factorial of n, Q factorial of a1, Q factorial of a2, and so on up till Q factorial of an. Okay, so this is what I'm saying, that when you want to define the Q multinomial coefficients, oh god, handwriting. Q multinomial coefficients, then this term with a sub q here is actually the Q factorial of n divided by product of Q factorials of these numbers a1, a2, an, where the Q factorials I have defined where the Q factorials have been defined in this fashion. So Q factorial of any number is this huge product instead of a 1 into 2 into 3 and so on up till n. Okay, so it's a product of these polynomials. Is this fine now, Agla?
Yes, ma'am.
Saham and Ridhiman, fine?
Yes.
ma'am.
Okay, so once we understand this notation, now let's come to the proposition at hand, which asks you to prove the number of k-dimensional subspaces of the field FQN, where Q is any prime power. So people understand prime power, right?
Yes, ma'am.
So it just means that Q is equal to power of a prime number. Okay. In particular, it could be a prime number or a power of a prime number. So that's what a prime power means. So if Q is any prime power, the number of k-dimensional subspaces of the field and FQ is a field with Q many elements, and then you have taken product of FQ with itself n times, and that is how you get the field FQN. Okay. Is it fine?
Ma'am, F is the field with Q many elements. FQ.
Sorry.
Is FQ the field with Q many elements? Like I, I I thought that um, it is a field if Q is a prime. Is it true for a power of prime as well?
Yeah.
Okay.
So it asks you to actually count the number of k-dimensional subspaces of this field, and the result you already know is that it is the Q multinomial coefficient n choose k. Okay, but you have to prove this. So suppose Gnk is the number of k-dimensional subspaces of Fqn. Then this is really the number which you want to compute, correct?
Yes, ma'am.
Okay, and Nnk is the number of ordered k tuples v1, v2, vk of linearly independent vectors from this field. All right. So
Yes.
defining these two terms now, in how many ways can v1 be chosen from this?
It can be any non-zero vector.
Any non-zero vector. So this in short has q raised to n many elements, right? So the zero vector is the 0, 0, 0, 0, 0. Therefore, the choice for v1, because you want to choose linearly independent vectors, v1 in itself cannot be a zero vector. Therefore, v1 can be chosen in q raised to n minus 1 ways. You have to take off the 0. Okay. Now, once v1 has been chosen in these many ways, v2 can be chosen in qn minus q many ways, right? Because v1 would have made q many vectors dependent on this, dependent on itself. So v raised to 2, v1 square, v1 cube, and so on, everything is ruled out. Oh, sorry, I think I am wrong. Just a second, just a second. Yeah, okay, sorry. So what I really meant to say here is that so this is the product of FQ n times, right? So once you have chosen V1 to be any non-zero vector, then the V1 coming from one particular layer as in FQ raised to n has n many layers, right? So if you see it through as a, so to say, a lattice, once V1 has been chosen, Q elements are dependent on V1, which would lie in the same layer of the FQ. So those Q elements have to be eradicated when you are trying to choose the next vector, which has to be independent of V1. So to choose V2, there are Q raised to n minus Q many ways. And then when you come to V3 has to be chosen from this particular field, from this space in such a way that it should be independent of V1 as well as V2. So there are a total of 2 layers which you have to get rid of, which means V3 can be chosen in Q raised to n minus Q square many ways. So there are Q square many elements which needs to be removed from the set. Okay, so in this way you choose your k many elements in this particular to make a k tuple v1, v2, vk. So the number n is the product q raised to n minus 1 corresponding to v1 corresponding to v2 q raised to n minus q2 q and then qn minus q square and so on till qn minus q k minus 1. Okay. So this was about the k tuple v1, v2, vk. But in how many ways can you choose a k-dimensional subspace of this? There would be many k-dimensional subspaces, and that is what you have to find. But in how many ways can you make this choice? So to make this choice, you will have to first start with choosing some subspace W of this, which is of dimension k, and then in this, you have to fill in k many elements, which are these elements. So once you have taken a W in GNK many ways, you will choose V1 in this W in Q raised to k minus 1 many ways. Right? Because it's a total of these many vectors which are there. And so from this, now it is restricted to FQK. Because now you have fixed your k-dimensional subspace. Once this is chosen, you will have to find V2 in this, and again the same logic, you will have to remove the Q elements which are now dependent on V1. So for V2, there are Q raised to K minus Q many ways available inside of W, and then so on till Vk. So the number n is actually also the number given by GNK multiplied by these possibilities, which is q raised to k minus 1, q raised to k minus q, and so on till q raised to k minus q raised to k minus 1. But these are representing the same number, right? Equation 1 and 2. Yeah. Are we connected? So we
Yes,
will
ma'am.
equate both of these and see that G and K turns out to be this entire equation divided by this entire equation. Okay, so this is Gn minus 1, Gn minus q, and so on divided by this entire thing. And this I directly wrote as this, but for this, so if you just remember it a little, this is what your G and K is. And with this notations in hand, So gn minus 1, gn minus q, gn minus q, k minus 1. Okay. Yeah, so this is correct. Now, I just do little more manipulation here. So instead of q raised to n minus 1, I will write 1 minus q raised to n, minus of 1 minus q raised to n. Okay, so I take a minus out of this bracket, minus out of this bracket, and so on till minus out of this bracket. How many minus do I have? Minus 1 raised to k. How many brackets are there? K many brackets, right?
Yes.
And similarly in the bottom, in the denominator, there are k many brackets. So this entire equation, or rather this rational function, can be rewritten as 1 minus q raised to n, 1 minus q raised to n minus 1, and so on. And why all this appears to be 1 now? Because from this bracket, I take a q out. From the so the q which comes out of this bracket and the q which will come out of this bracket cancels out. Okay, so after a q comes out of this bracket, I'm left with q raised to n minus 1 minus 1. And then with the sign change, it's actually 1 minus q raised to n minus 1, which is here. And similarly here, it would be q raised to k minus 1 minus 1. And then with the sign interchange, it is 1 minus q raised to k minus 1. Okay, so these sign interchanges gives me this. These sign interchanges and a q out gives me this. And then in the next bracket, you will have a q square coming out and a q square coming out in the bottom as well. You do the sign change, you will get that. Till the end here, q raised to k minus 1 comes out from top and bottom both. And you do a sign change to get 1 minus q raised to n minus k plus 1 divided by 1 minus q, right? There is just a q difference here. Is that right?
Yes, ma'am.
Okay. So far, so good. Now, everyone knows the expression for what is a square minus b square? Yeah. Expansion of a square minus b square?
A plus B into A minus B.
A plus b into a minus b. And if you have a extension of this, what is 1 minus b square?
So 1 plus B times 1 minus B.
Right. And 1 minus b cube? So whenever you're dealing with 1 minus b raised to k, you certainly know that b is a factor of this. So 1 minus b is definitely a factor. As in b equals 1 is a root. So 1 minus b is a factor of 1 minus b raised to k for any k.
Yes.
Any k positive. So in short, and what is really left once you divide, I mean, if you do the division algorithm and you divide 1 minus b raised to k by 1 minus b, what is left? What's the quotient? It's okay, just speak. At max, it would be wrong.
It's 1 plus B plus up to B power n minus 1.
Great. So whenever you are dealing with a 1 minus b raised to n, it can be factored as 1 minus b times 1 plus b square and so on till b raised to n minus 1. So using that observation, or rather that particular expansion, 1 minus q raised to n can be written as 1 minus q times 1 plus q square and so on till q raised to n minus 1. Similarly, this can be expanded. Similarly, this can be expanded. When you expand, so a 1 minus q from here and a 1 minus q from here cancels out. Similarly here, and here it's just a 1 minus q. Excuse me. So when you do the expansion for this, the 1 minus q from this cancels out with this one. So the last term here actually is just the 1 plus q, which would have survived from 1 minus q square, right? And you get this. So this particular term leaves this as your quotient, this leaves this as your quotient, and so on. This would have left this as the quotient. This particularly vanishes, so there is nothing which would have corresponded to this. However, this corresponds to this comes to this, and the one just before this, which was 1 minus q square, gives you 1 plus q here. Okay. Now just compare this particular thing. So if you try to read it from here, it is 1 plus q times 1 plus q square and so on till 1 plus q raised to k minus 1 with this term. Then what do you get? Yeah, what is this particular denominator?
Q factorial of k.
It is the q factorial of k. That is right. Now in the numerator, what do I have? I have something till q raised to n minus 1, but it's starting from n minus k. The highest power of q is n minus k and not 1, right? So as we have done in high school, we do the manipulation of multiplying and dividing at the same time. So the rest of the terms, which are 1 plus q and so on till n minus q minus 1 times 1 plus q and so on plus n minus k minus 2 and so on till 1 plus q. This particular entire product of polynomials, I multiply here and I divide by it. But what is this polynomial actually? This is q factorial of n minus k. Isn't that so?
Yes.
Right? So what I have effectively done is that I have taken n minus k, q factorial of n minus k, and when now this particular polynomial producted with these many terms, it's actually the q factorial of n. So this entire manipulation is q factorial of n divided by, so this is the term which is taking care of these terms. So this is q factorial of k times q factorial of n minus k, which is by definition the q multinomial coefficient n choose k, or n choose k comma n minus k. Okay. And hence, what we were asked to prove here is done, because till here we deduce that g and k happens to be this, and then when you manipulate further, you get that this is actually equal to q multinomial coefficient n choose k, or rather n multi choose k. Okay. Exercise in this line, that if this is defined to be this, which is the q multinomial coefficient, we have already talked about this, then show that the Q multinomial coefficient can be written as the product of these Q binomial coefficients. So all these are binomial coefficients, right? Right?
Yes.
So the Q binomial coefficients together in this form gives you the Q multinomial coefficient. Okay. And the Q binomial coefficient n choose k appears as the sum of these two Q binomial coefficients. Remember, if you were, instead of a Q binomial coefficient, if this Q was 1, this actually still matches up. Because n minus 1 choose k plus n minus 1 choose k minus 1 is n choose k, right? That's a very standard identity.
Yes.
However, if you're dealing with a Q which is not equals to 1, the Q binomial coefficient n choose k turns out to be Q binomial coefficient n minus 1 choose k plus there is this additional multiplier to this term. Okay, so these two identities are a homework for you. Will come in the assignment. Now we revisit the partition of n. So, so far, whenever we dealt with the partitions, we just said that, or rather compositions, we always called it, correct? We said compositions of a natural number. So we were looking at how we could represent a natural number as a sum of numbers which are less than equal to this number, right? Now we put little more restriction to this and we say that instead of doing any sort of addition, so for instance, 3 could be written as 1 plus 2, 3 could be written as 2 plus 1, 3 could be written as 1 plus 1 plus 1, and all three were different compositions, right? Right?
Yes.
So now we are interested only in those compositions of the natural number which are written in the non-increasing sequence. So the composition 1 plus 2 is no longer valid for me. I'm going to consider only the compositions 2 plus 1 because 2 is greater than equal to 1, and the composition 1 plus 1 plus 1 because 1 is greater than equal to 1 greater than equal to 1. Okay, so that is it. So lambda equals to the sequence lambda 1, lambda 2 and so on of integers lambda I such that their summation is n, and the condition lambda 1 is greater than equal to lambda 2 greater than equal to and so on greater than equal to 0. So of course you are taking non-negative integers. Okay, whenever you're doing the partitions or compositions, you never deal with negative numbers. And why 0 here we will see in a moment. So such a thing is called a partition of n, and you write lambda to be lambda 1, lambda 2, lambda k if anything after this is 0, which means lambda k is the last element which is non-zero, or rather which is positive. Okay, and of course you know lambda 1 is greater than equal to lambda k because of this ordering, right? So
Yeah.
in that fashion, I know that lambda is unique. Meaning, once I get rid of the redundant zeros at the end, there is a unique way of writing this particular partition. And when such a thing is there, you denote it by this, that lambda is a partition of n, or that mod lambda is n. Mod lambda makes more sense in the way that the elements of lambda sum up to n. Sum to give you equals n. Okay, so if you have any lambda to be 3, 3, 2, 1, 1, 0, 0, and everything is 0 now onwards. So this is actually, the interpretation is 3 plus 3 plus 2 plus 1 plus 1 plus 0 plus so on. So this is going to be same as 3 plus 3 plus, or rather 3, 3, 2, 1, 1, 0, 0, and you put a bracket here. So you could safely put a bracket here using this data, right? Or you could actually put a bracket here as well for the same logic. They represent the same lambda, because anything beyond this is 0. Or even better, you could put a bracket here. And this is the sort of most restricted form in which lambda could have been attained. All right?
Yes.
So, where is it? So these are all partitions of 10. Why I know the partitions of 10? Because 3 plus 3 is 6 plus 2 8 plus 1 9 plus 1 10. So summation of these entries gives you number 10. Therefore, it's a partition of 10. Now, I've already said what is the difference. So this symbol here means between. What is the difference between a partition and a composition of a natural number? That here parts are written in a non-increasing order. Okay, so or rather a weakly decreasing order. However, in a composition, order in which the parts would have appeared makes a difference. So 1 plus 2 was different from 2 plus 1. So here you had all possible partitions. I should not say partitions. Compositions includes all the ways in which a number can be written as a sum of non-negative or rather positive integers. However, partition is the way of writing a natural number in the fashion such that elements appear in a weakly decreasing order. Okay, so clearly every partition is a composition. However, every composition will not be a partition, right? Is that right?
Yes.
Okay. Now, if you, this lambda was equal to a sequence, lambda 1, lambda 2, and so on. So if you're dealing with any particular n, in short, if this n is determined for you, then the sequence lambda equals lambda 1, lambda 2, lambda blah, blah, blah has to terminate after a point, because this summation has to be n. So it cannot happen that infinite many terms of this, I mean, this is achieved for sure. And you even know that lambda I is certainly 0 for I equals n plus 1. Because the largest number of elements you can stuff in here is 1, 1, 1, 1, 1, 1, 1, 1, 1. And how many positions will that block? Exactly n many positions, right? The smaller the denominations you use to write your number n, the larger the number of blocks will it occupy here, correct?
Yes, ma'am.
So certainly lambda of n plus 1 is 0. Right?
Yes.
Great. So once you have done this, coming down to this, so the non-zero parts, or rather non-zero lambda i's, which are there in this particular sequence are called parts of lambda. Okay. So clearly, if you have hit a 0, you cannot hit anything which is non-zero because of this condition. Which means if a 0 has been hit, everything after this has to be a 0. Right? Therefore, the parts which you are seeing here are exactly the first non-zero elements that appear in this sequence. Correct?
Yes, ma'am.
People seem to be confused, or I don't know. I mean, I'm hearing very little sounds. So is this clear that the lambda i's, which corresponds to non-zero entries, they are called parts of lambda, and then length of lambda is nothing but the number of parts of lambda, which means the number of non-zero entries in lambda. Okay. Now,
Okay, ma'am.
remember, all this we are really doing or are able to do in the sense that this 3 is repeated here, this 1 is repeated here. So these are coming from a multiset. The entries of lambda, or rather lambda, is a permutation of a multiset. Okay. So if lambda, let's say, has mi parts which are equal to I, then you write 1 raised to m1, 2 raised to m2, 3 raised to m3, and so on. So it is quite possible that there are some, so for instance, if you see here, there was nothing which was 4. So if lambda has mi parts which is equal to 4, then mi has to be 0. So m4 has to be 0. Right?
Yes.
Similarly, m5 is 0. M6 is 0. Because there are no parts of this particular lambda which are equal to 4 or 5 or 6 for that matter. So when you write lambda in this particular fashion, you put, whenever those elements are 0, you skip them. Okay. So for example, if I take this 4, 4, 2, 2, 2, 1, then how many parts are there which are equals to 1?
1.
1. How many parts which are equal to 2?
3.
So M1 is 1, M2 is 3. What is M3?
0.
M4?
2.
M5?
0.
M6?
Everything else is 0.
Everything else. Every higher MI is 0. Because the largest number here you hit is 4. So anything beyond M4 is 0. Okay. So now this lambda now is rewritten in the form of 1 raised to m1, which was 1, 2 raised to m2, which was 3, 3 raised to m3, which was 0, and 4 raised to m4, which was 2. And now, since 3 raised to 0, now don't see this as 1. 3 raised to 0 is not 1 here, because that is not the interpretation. Interpretation is that it is counting the number of times the number 3 appears in the partition. So you skip this altogether. Okay, so this number gets skipped, and 1 coming just once, so you write it as 1 instead of 1 raised to 1. So this then is rewritten as 1 comma 2 raised to 3 comma 4 raised to 2, and this is the partition. This is a partition of number 15. How 15? It's not 2 raised to 3, it is 2 plus 2 plus 2. So it is 2 into 3, 6, 4 into 2, 8. So 8 plus 6 is 14, plus 1, 15. So it's a partition of 15. Okay. Now, some notations. I'm sorry. This is fine now. Okay. So now if you so there are a few notations, and then we'll do quick computations with them. So if Pn is the number of partitions of n, total number of partitions, okay, Pkn to be the number of partitions of n with k many parts, which means the lambda corresponding to this partition has to have k parts, k non-zero elements in this sequence. All right. And then Pjkn is the number of partitions of n which have at most k parts, and the highest part has the value at most j. What is the highest value in my lambda? It is occurring at the first location, which means lambda 1 is at most j. So keeping these three parameters in mind, if let's say I give you n equals 5, and I ask you to just forget about this part. Oh, there is no way I could have made this. Oh, there is no way to blacken it completely. I mean, I can't hide it from you people. Possibly after 10 times. Okay, great. So first of all, if n is equals to 5, oh goodness, what is happening? I'll just stop my share and come back. Where is this? Yeah. So, okay, I'm not doing any drawings here. Some random windows pop up. So 5 can be written as, in the non-increasing way, 5 or a 4 plus 1 or a 3 plus 2 or a 3 plus 1 plus 1 or 2 plus 2 plus 1 or 2 1 1 1 1 1 1 1 1. Okay, I have not put a plus here, but these are the possible lambdas, correct? For the integer 5, right?
Yes.
So now, how many partitions of 5 are there?
7.
7. 1, 2, 3, 4, 5, 6, 7. 7 partitions are there. Next question. What is P1 of 5? So this is pkn, number of partitions of n with k parts. So how many partitions of 5 are there with just one part?
1.
1, which is this, right?
Yes.
And then how many partitions of n are 5 are there with 2 parts?
2.
Which are these, correct? It has 2 parts. How many partitions with 3 parts? 2 of these, correct? How many partitions with 4 parts? Only 1, which is this. And how many partitions with 5 parts are there? Is that right?
Yes.
So number of partitions with just one part is 1. So for k equals 1, this pk5 is 1. Number of partitions with 2 parts is 2. Number of partitions with 3 parts is also 2. Number of partitions with 4 parts is 1. Number of partitions with 5 parts is 1. Correct?
Yes.
Now, if I ask a little harder question, which is how many partitions of 5 are there which have at most 2 parts and the largest element is at most 3?
1.
1. Which is that element?
The third one.
3, 2. Everyone else also sees this? So how many partitions with at most 2 parts? So you have to see only among these 3 elements. And then the next condition is that the first part has to be at most 3. How many elements here with first part at most 3? Only this one. So 3, 2 is the only partition which qualifies, and therefore the number of such partitions is 1. Similarly, if I ask you the number of partitions of n with at most 3 parts, with first part being at most 3.
3.
3. So these are, the entire drawing messed up. So at most 3 parts, which means you will be looking at partitions from here till here, correct? And then you are saying partitions with at most, whose first element is at most 3, which means this, this, and this, correct? Because your first element is 4, which is higher. First element is 5, which is also higher. So there are 3 such possibilities. Fine. So P335 is 3. What was that? P325 will be 1, which we computed earlier. As convention, we fix P0 of 0 and of P0 to be 1. Okay. Okay. Now, here we saw a few things. So we did this earlier also. If you take any natural number and you take some n pockets for it, because at max n pockets can be filled here, that we know for sure. And all n pockets can be filled if and only if lambda 1 is equal to
1.
1 and lambda n is equal to
1.
1, which means all n pockets corresponding to a partition of n can be filled if and only if the sequence lambda is 1 1 1 1 1. All n, it's a 1 n times, right? Which means given the natural number n, if I ask you how many partitions of n are there with exactly n parts, the number should be So the question in this notation I'm asking is what is Pn of n?
One.
Everyone sees that? Yeah. Also, how many parts are when can this happen that the number n has a partition with exactly n minus 1 partitions? What will be lambda 1 corresponding to such a partition? Come in this thing. So n is 5. So I am asking about the partitions of n with 4 parts. So how many partitions are there with 4 parts, by the way? See here. So this corresponds to the partitions with n minus 1 parts, right? And how many such partitions are there? Which is this partition corresponding to? 2, 1, 1. Correct? If instead of 5, I ask you for n equals to 10, what is the partition? How many partitions are there that correspond to 9 parts? See, you saw this particular line, right? So this was all ones and it had exactly n parts. Now you have size for one less part. And then you know that the numbers have to be written in non-increasing order. What can you do in such a scenario? When you have all ones, you could have just added these two up. Correct? And that's how you'll reduce one particular part. There is no other way. You see it.
Yes, ma'am.
So the number of partitions of a natural number n with exactly n minus 1 parts is equal to
1.
1. And what is that partition?
2 followed by 1.
2 followed by ones. N minus 2 many ones. So that is exactly the number. Now, another thing, if I ask you how many how many partitions of n are there with exactly one part?
1.
1. Because till now you were dealing with exactly n parts, so you were at the bottom. Now you said that exactly one part, so you're at the top, and it's exactly the way the number itself is written. And 5 is equal to 5, right? So P1n is same as Pnn, which is equal to 1. Fine.
Yes.
Okay. Now, another interesting thing, or maybe all this was quite trivial. If I ask you, what is P2n? How many parts, how many partitions of n are there with exactly 2 parts? So at least in this case, where are these examples? These are the 2 examples.
Floor of n minus 1 by 2.
Floor of n minus 1 by 2. Okay. So let's say I deal with 6. Then how many 2 partitions are there for 6?
Oh, sorry, one C.
Hmm?
3.
3. So that does not match with your answer.
It should be seal of and that.
Seal of n by 2. Why? Very nicely we can see in exactly half many ways you will have the way to choose this first number, right? You cannot peak it up by that, or rather if you see from this side, when you have exactly 2 parts and you know that this part has to be larger than this part can be at most n by 2. Isn't that so? It's actually floor of n by 2 here. And as soon as this integer is determined, this integer is automatically determined. Right?
Yes.
So if I was working with a 5, I had the choices here to be put as 1, 2, 3, 4, 5. But 5 cannot be chosen. So I could have chosen 1, I could have chosen 2. If I choose a 3 here, then to make it to be 5, I would have to put a 2 here. But then that will not be a partition. So the choices here I have is 1 and 2. And so what this really means is that you can hit up till half of this, but you cannot go above that. 3 was more than half of this, right? So you take a n by 2 with a floor. Okay. So, and as soon as the choices for these elements are fixed, choices for these elements are automatically fixed. So you have counted the number of partitions of n with exactly 2 parts, correct? And that is equal to floor of n by 2. Oh, okay. I've made a mistake here. This is a floor function. not the seal function. You're dealing with the floor. So all this we understand now. Now this is another exercise for you. Just how we did for the compositions, here also we have a recurrence relation, because ultimately, even if we try to forget, we should not forget. We are dealing with working with generating functions. So here and there, we will look for recurrence relations, and then we will want to solve those. So the pkn, which we defined here, satisfies this recurrence relation. This is another exercise which you people will do. And now we come to Ferrer's diagram. So we did we fixed the partitions to be in the notation that they appear in non-increasing order. So lambda 1 is greater than equal to lambda 2, greater than equal to lambda 3, and so on, right? So if this is a partition of n, you draw left aligned array of n dots, which has exactly lambda I many dots in the ith row. Okay, so if let's say I take 5, 5, 4, 2, 1 to be a partition of 17, so it's 5 plus 5, 10, 14, 16, 17. So okay, that's not a mistake. So if this is a partition of 17, you take this array left aligned, which means all the arrows you start drawing from the first column. Okay, so first you draw 5 many dots in the first row, so 1, 2, 3, 4, 5. Then next in the second row you draw 5 dots again, so 5 dots are there. Then you draw 4 dots, which is here. Then you draw 2 dots, which is here, and then finally 1 dot, which is here. Right? Oh, I've written already here. Okay, so 5 dots are there here in the first row. Second row has 5 dots. Third row has 4 dots. Fourth row has 2 dots. Fifth row has 1 dot. Okay, so such a diagram of dots is called a Ferrer's graph or a Ferrer's diagram of lambda. Okay, and instead of dots, if I drew squares like this, then this is called a Young diagram. You people might have come across Young tablex, etc. in different contexts, because it's always represented through squares. The name is Young. Young as in not the young in the sense of old and young, young in the sense whenever the diagram representation comes through squares. They might be representing different things. Here, Young's diagram represents the partition of a number. And so instead of 5 dots, you have 5 squares here, 1, 2, 3, 4, 5, followed by 5 dots, 5 squares, then 4 squares, then 2 squares, and then 1 square. Okay, so something like this is a Young diagram. And you should now prove that. So this is a very nice, way of putting things into perspective of what we have already learned. So recall this PJKN is the number of partitions of n, which has at most k parts, and the largest part is at most j, right? That is the notation for PJKN here. Okay. This summation q raised to n. So this you see is actually so to say, it's a recurrence relation, not recurrence of, what am I saying? Generating function. So this is a generating function for PJKN. Okay, and the value turns out to be q binomial coefficient j plus k choose j. Okay. Is that okay?
Yes.
So this is another exercise. Now, we move to the last topic of this unit, which is partition identities. So here we will, so obviously, I mean, already we have been dealing with different ways of partitioning and different representations for the partitions of a natural number. Now we will have several identities where we will use generating functions to prove these identities. So mostly it'll be like using the generating functions, and the method of proving them would be the combinatorial way. Okay, so just a glimpse into it and I'll end. So the Ferris graph which you drew here, it has some nice property. Can someone tell me quickly?
The total number of dots is n.
Sorry?
The total number of dots is n.
Total number of dots is definitely n. We called it an array of n dots. So the number of dots in this array has to be n. Similarly, the number of squares in, okay, so since you guys are all Olympiad people, I do not want you to say that this is also a square. No, I'm dealing with just the 1 cross 1 square. So this Young diagram here has n 1 by 1 squares. But another interesting thing is that each subsequent row has lesser elements than the previous one. You would say, ma'am, that's pretty much obvious because the lambda which we choose here is exactly in this fashion. Agree. And that's precisely the point we want to emphasize upon. So since second row cannot have more elements than the first row, and so on, what you also know is that second column cannot have more elements than the first column. Correct? Because there are no redundancies in between, right? So it could not have so happened that there was nothing here, and then while I started drawing here, there was something here. I kept it left aligned, right? So the
Yes.
structure which is actually drawn like this also gives me some information if I drew it like this. Instead of row wise, I could have drawn it column wise. And that's what is called a conjugate. So, oh, I did not even scan the next page. Sorry. So there was one more page in my notes. Okay, so it's okay. That can stay here. So when you take, so there is this main diagonal here of this array. If you take the reflection of this particular Ferrer's graph along the main diagonal, what you get is also a Ferrer's graph or a Ferrer's diagram, and it also corresponds to a lambda, a different kind of, a different lambda. Again, a lambda corresponding to 17 in this case, but so for instance, here it was, when I started from here, it was a 5, 5, 4, 2, 1. If I do it this way, it's going to be 5, 4, 3, 3, 2, right? Right?
Yes, ma'am.
So the question which I have listed here, so what was special about Ferrel's diagram or Young's diagram? They were of course left aligned, and hence you could take a, if you take a reflection about the main diagonal, it is also of the same form. Does it also represent Ferrel's diagram of lambda? For some other partition lambda? Yes, we have already seen this. So for instance, if this is the particular example we take, it would have corresponded to 5, 4, 3, 3, 2, right? And since Glenn already has pointed out that it has exactly n dots, whether you counted this way or you counted this way or you found any other funny way to count it, the number remains n, which means the new lambda prime which you have got is also a partition of n. It is a legitimate partition of n, not just some numbers which are adding up to n, but because of the left alignment, you also know that lambda 1, or rather, let's say if what you got new thing as lambda prime, then lambda 1 prime is greater than equal to lambda 2 prime greater than equal to lambda 3 prime, and so on. And thus, this lambda prime, which you achieved from lambda by reflecting along the main diagonal, is also a partition of n. Okay? Is that okay?
Yes, ma'am.
So there are a couple of identities which are there in this section. I'll put up a write-up for this, and yeah, there are many exercises. They all I'll put in your assignment sheet, and Sunday we are meeting for the quiz. Okay, so I would be emailing each one of you with the Google link, Google Meet link, and you have to join there. Okay, just a reminder, quizzes of 30 minutes duration. You should WhatsApp me your solution within the stipulated time for each question. Fine. Keep some A4 sheets ready with you with your name written on each of the sheets. Okay.
Okay, ma'am.
Okay, that's all for today. Any questions? Any questions?
No, ma'am.
Others?
No, ma'am.
Okay, then I'll end the lecture here. Okay, see you.
Thank you.